So, good morning, guys. I hope that you guys are getting prepared for the holidays and you're not too burdened with too much work. I don't have any attendees right now, but I'm going to go ahead anyway. I think Thursday's session, last week, a couple of sessions that I did last week, probably more relevant to the exam, and I think you guys probably are most focused on that now. I notice a lot of people are working on it, and have been a number of submissions already. So, and the grades look pretty good. So I'm going to go over the last couple of segments I wanted to review. They're not so relevant to the exam since the exam covered primarily analysis of variance and correlation and regression. But I just wanted to cement in this last part again, some of the material we did earlier in the semester, so that you remember that what we have in statistics is a series of tools, and these tools have specific applications. So when you, and as you go on in your career and your academic career and your career outside of school, as you go on and you're confronted with issues where you have to evaluate, analyze data, keep in mind that the nature of the data, the type of the data, really impacts on which of these tools is appropriate to use for it and what circumstances that you can use it, what assumptions you have to make, what kind of data it is. So it's not surprising, considering that we started the semester spending quite a bit of time on evaluating what data types we're going to be working with. What's a categorical data? What's numerical data? What's scalar? As SPSS calls it, scalar. And from that point, once we understood the different data types, then we went into the various statistical tools that we would work with on those data types. So one of the things that we worked with was the idea, really at the very beginning, the idea of estimating the mean of a population. Okay, now a mean represents the middle, basically, of a numerical variable. In other words, the average number in a variable that's a series of numbers, a scalar set of numbers. Okay, so I'm going to demonstrate that in the community health survey. In the previous videos, we talked about how to access the community health survey. We have a copy of it posted online on Blackboard. So I'm going to go in here and I'm going to take a look at the community health survey. Well, interestingly enough, let's see, what do I have here? I'm going to go into my variable view, and I have over 200 variables that were collected from over 8,000 people in New York City in this particular set in 2013. So since I'm talking about finding a confidence interval, and from that, perhaps comparing a mean of that population to a mean of another population, I'm going to be interested in scalar or numerical variables, and you can see them here. So now SPSS will allow me to sort data by different measures. So I'm going to see, could sort by, let's see if I can't sort by, okay. Sort ascending, okay, let's see. I'm going to click sort ascending, means the A's are at the top. Okay, I don't want to save this. Okay, so let's see if that worked. Nominal variables. Oops, I saw scalar variables there. Oh, actually, it didn't sort, did it? Let's see. Let me try this again. Do you want to save the current pre-sorted variable order in the new attribute? No. And did it sort it this time? I think it did. Yeah, there we go. We're sorted now. Okay, so let's look at these scalar variables. One of them, this one in particular, let's see what the question that's associated asks. Oh, what's your age? So that's the individual's age. Next one happens to be a unique identifier for that particular individual. This next one is actually a misidentified a categorical variable, which is 34, a number representing 34 different neighborhoods. Next one, number of cigarettes smoked every day. And let's see, every day, continuous for missing and adjusted, per day smoked, number of cigarettes smoked per day, every and some day smokers. Okay, that's only within a certain subset. So this one, number per day is the number of cigarettes an average smoker smokes per day, and this one represents the person's age. So I could take either one of these things, and since they're numerical variables, I can find a confidence interval, and I can use them later to compare it to other means. Now I'm going to work with age just as a simpler spot to start, and there's more data, more people reported their age. So if I want to know, if I want to estimate the mean age of this entire population, well, I'd either have to have a census, go around and ask everyone their age, or I would have to take a sample from that population, and based on that sample, calculate what the average age of that sample is. Once I know the average age of the sample, and I know the variability of ages within that sample, I can predict with whatever level of certainty that I want, very frequently 95% certainty, hence 95% confidence interval, I can predict what range within I would expect to be right 95% of the time in predicting what the population mean is. So I'm going to give that a try. I'm going to stay on that variable here, and I'm going to say analyze, and I'm going to go into descriptive statistics, and I'm going to go into descriptives. I'm going to ask it to tell me for that variable, which is, let's see, demog. Let me see if I can't find it now. It would be nice if SPSS would highlight these variables. Okay, it's down here. Okay, then it was your age. Good. Okay, now I'm going to go in here and I'm going to say to myself, okay, we want to calculate the 95% confidence interval, and we want to find the mean to start off with. So here we are. I'm going to add variance in here, and SPSS will calculate all of these statistics that are relevant to this sample, to a numerical sample. I'm going to click OK, and let's see what I wind up with. So the mean of this sample is 49 years old, 49.19 years old. And the variability of this sample, the standard deviation and the variance, is 17.5 years. So it's quite variable, quite a wide range of ages in this population. In fact, I'm going to go back here now again, and I'm going to analyze descriptive statistics, and I'm going to go into explore to get a bit more information about this population. Okay, again, I'm going to go down to my sorted scalar variables. Oops. Let me get to them. There we go. Select that variable, age, put it in there. I'm going to click into statistics. Well, Explore is going to actually calculate a confidence interval for me. And we remember the confidence interval is based on the mean and the standard deviation. So in this case, with a very large sample, the confidence interval would be the mean, 49 years, plus or minus 1.96 for our 95% confidence interval for a normal distribution, times the standard error, and that's associated with the standard deviation of the population and the sample size, as we recall. So SPSS will calculate this for us. Go ahead and say calculate it. Let's say OK, continue. And while I'm at it, I'm going to ask it to produce a histogram for me as well. The dirty little secret in SPSS, whenever you use Explore, it's going to calculate, even though it wasn't in plots, it will calculate a box plot for you as well, okay, even if you don't ask for it. So I'm going to make sure I display both, which is the statistic results and the graphical results will come out in my output. So I'm going to click OK. And of course, as we've seen, the output window will come to the front, and we'll see the coding that SPSS uses to describe that operation in its macro language. Okay, and then we'll see our result. So we can see the mean is 49 years old, and the 95% confidence interval is 48.8 to 49.56. Well, it's interesting that with all of the variability, the standard deviation was 17 years, right? A lot of variability in this population, right? 17 years. That 95% confidence interval would only have a very narrow range like that, right? And it's interesting that such a narrow range would be associated with standard deviations. That's so big. So, just for as a thought process, what do you think might have led to the standard deviation? Excuse me, the confidence interval being so narrow. And of course, if you look closely, the reason why the confidence interval is so narrow is because even though it's a big standard deviation, it's a relatively small standard error, and the standard error is very small because the sample size is so large. We rarely get into many situations where we have that big a sample. Hi Ben, how are you doing? I see that you've logged on. I'm gonna if you have a microphone, I'll activate it. But if not, you can talk. You can talk with me in the chat box. Okay, so I'm gonna go ahead and move on. So at any rate, so moving on. There's our box plot, shows our range of values, right? The oldest person was probably somewhere around 98 years old. The youngest person, now keep in mind that we have not surveyed everybody in the population, right? The survey is only done on people that are 18 years of old and older. So we're down here. So and you'll notice that in our histogram, even though it looks like it should have been normal, but we're cut off there. Again, we're missing that part of the distribution, right? So our mean is a little bit compromised here in terms of the entire population. So it would be mean of the population that's greater than 18 years old. Okay, so at any rate, Ben, for your sake, what I'm doing is I'm going back over the earliest part of the semester, just as part of a three-part series of these uh, um, uh, sessions for the last week, where I kind of review what we talked about during the semester, and the tools that we've learned how to use and where to apply them. And on Thursday, just about the time I posted the final exam, or just after I posted the final exam, we covered correlation and regression. And most people showed up, and most people were more interested in that, certainly, than this, because this part was not on the third exam, since it was material that we had earlier. Okay, so that's the way we would calculate a mean for a numerical variable and the confidence interval for a numerical variable. So I'm going to go on a bit. If you have any questions about general questions about the material on the exam or during the semester, you can go on and ask me. This will be posted later on so that everybody can take a look at it, or skim through it if they're interested. And I can answer general questions like about correlation, regression, about the other material that's on the exam, analysis of variance. Although I can't answer specific questions, obviously, on the exam, except to clarify something. Maybe there might be something I can do to help if you're having an issue with that material. So at any rate, so let me go back to this. So we have a confidence interval, we have our box plot. The other thing that we can do now, since we have this tool that'll work with numerical variables, and the the point estimate, the mean for that numerical variable, now that gives me an in to being able to compare this mean to the mean for another population. So I'm going to go back and take a look at my data again. And my data, here's my numerical variable, right? I'm going to go back up here and see if I can't find something relatively simple. And let's see, a numerical variable that's relatively simple. Here's one that says, let's see, general health. How about this one? Insured. Okay, type of health insurance. Insure gateway. Let's see what that one says. I believe that's a numerical variable that will tell us whether a person is insured or is not insured. Okay, so I'm going to, let me go back to the data view. That's the 19th one across. Let's see if that's what that looks like. Okay, demography. Insured gateway. And indeed, that looks like ones and twos. I'm going to go now back to the code book for this data set. And the code book, of course, is going to tell us exactly what each one of these variables represents and what the values that they put in here, what that 1 and 2 represents, for instance. And to speed things up, I'm just going to search for it. Insured. Here we go. Insured gateway. Do you have any kind of health insurance coverage, including private health insurance, so on and so forth? So basically, it's a yes or a no. 1 is yes, 2 is no to the question, are you insured? So a lot more people are insured than not insured. But at least now we know what that variable is. This 2013 was, I guess, just before, was after Obamacare, I would guess, right? So, or maybe on the cusp of people signing up for it. So perhaps the insurance rate's a little bit higher now. So let's go back here. And now that I know that's the case, I'm going to go back to my variable view. And I'm going to go in here and I'm going to make sure that we know, or SPSS knows, oops. I'm going to make sure that SPSS knows that the values that are represented here, 1 means insured, and 2 means uninsured. Okay, and click OK. Okay, so now when I go into my data view, okay, if I go back over here to approximately where that variable is, if I can find it again, there it is, insured gateway. Insured gateway. Now it's filling in for me the numbers that represent the values that represent the numbers 1 and 2. This, for instance, this individual is insured. The next individual, what may not have been, I just kind of clicked over and got away from that, but that's okay. I'm going to go now into analyze, just compare means, because now not only do I want to know, well, before I do that, I can do something else interesting. I can go back into descriptive statistics, into explore, just as I did before. In fact, my first variable, what is your age, is still there. And now I can go down to my categorical variable, which is insured, uninsured, I guess. Insured, uninsured. Yep, that's our variable there. Our variable, categorical variable, which is just basically insured and uninsured, 2 categories, and move that into the factor list. Okay, now that that's in the factor list, right, SPSS knows that we want to break up the calculations for this numerical variable, age, into at least 2 groups, because I'm separating those groups by a factor. I'm factoring or breaking them down into 2 groups, insured and uninsured. So I'm going to click OK. Well, first, let's go back up here. We're already set up there. Plots, okay, we're already set up there, and we know we're automatically going to get our box plot. So I'm going to click OK, and let's think for a moment. Do we think uninsured people on average are older or younger? Okay, well, we're about to find out. Okay, so let's see what we'll end up with. SPSS again brings up our output window, and as you can see, just as we saw before from our listing, 7,000 people are insured, 1,300 people, 1,400 people are uninsured, and this is the response rate. 3% did not respond to that question, and so on and so forth. Okay, so what's the average age of people that are insured? In this population, it's 50. What about the average age of people that are uninsured? 40. Wow, that's interesting. There's quite a bit of difference between the average age of the uninsured and the average age of the insured. Well, I can think of a few reasons for that, right? One reason is that almost everyone in this country that's over 65 is on Medicare, so they're insured. Okay, while younger people, they have to get private insurance or insurance from work and so on and so forth. Okay, so it's not that unusual. Also, younger people are more likely to bypass even Obamacare. One of the issues with Obamacare is that it really needs younger, healthy people to be financially secure, and that's a little bit more difficult. It's hard to convince younger people that they need health insurance. That might impact that as well. So now this is a sample. It's not actually everybody in the population. So we're going to want to know whether or not we can say with some level of certainty that mean for the mean for the population of insured and uninsured are really different. This is very interesting that we found that for a sample. What about for the entire population? These results might be due to chance. Okay, so, and we have a couple of histograms show us basically what the distribution looks like. Okay, it's a little bit skewed to the right there, right? Because we don't have the younger people included, under 18s included here, but we have some small portion of the population that's still hanging around there, a pretty old age. Okay, we aspire to be in that group there. So at any rate, and here's our box plots, and we can see that the uninsureds tend to be younger than the insureds. Look, 50%, the middle 50% are down here versus the middle 50% there. Okay, and again, the insureds go up to 98 or so. That old guy's up there, right? And again, he's probably has Medicaid or Medicare. Right? So it's interesting, but we haven't proved anything, have we, statistically? So I'm going to go back to analyze, except this time, what I want to do is I want to directly compare these. We've indirectly compared these means this way. I'm going to directly compare these means. So I'm going to go into compare means, and I'm going to go into independent samples, and I'm going to say, okay, we want to examine the test variable is the age, our average age. And my grouping variable, again, was my whether or not they were insured or not. Okay, let's see if I can find it. Wasn't that far down. Here we go. Insured, uninsured. I think that's average. Yes, I believe it is. Now, it wants me to define the groups because we use t-tests, compare means with t-tests for only two means. Okay, remember, analysis of variance was for multiple means, comparing multiple means at the same time, multiple samples and their means at the same time. For the t-test, we're only comparing two. So in case there's other variables in this data set, I have to let it know that the two that we're comparing are insured and uninsured, ones and twos. So I'm going to click OK. Our output window again is going to come to the front. And here is our summary box of the numbers of people in the study and so on, and the results. And here's our determination of our t-test. Well, the first thing that we know is that when we do a t-test, when we did it mathematically, when we use calculators, we know that we did it slightly differently when equal variances, when the variances of the two groups, the variability of the two groups were the same, versus when the variability was dramatically different between the two groups. Okay, so now we need to consider that as well. Now, if I look up here, let's take a look at the variability of these two groups. Insureds is 17, right? The mean age of insured is standard deviation of mean age of insured people is 17 years, and the mean age standard deviation for the mean age of uninsured people is only 13. It's a bit of a difference there. Let's let SPSS tell us whether we should consider these equal or unequal variabilities. Okay, and the way we do that is we go over here to Levine's test of equality for variances. That's these four boxes right here. That's what we're interested in. You'll notice that the t-test, see t is over here, the t-test is calculated twice, once in the top line and once in the bottom line. Okay, and the top line assumes equal variances. Equal variances assumed. You can see it right there. Just like many of the operations that we do in statistics, we're going to look at that. We're going to say to ourselves, our null hypothesis is that things are equal. There's no difference. So we're going to assume equal variances are a null hypothesis. And we're going to only reject that idea and go to the second row, equal variances not assumed, if this test for equality of variances tells us that we can do that with less than 5% chance of being wrong, with 95% certainty or less than 5% chance of being wrong. And where do I find that probability? I find it in here, the p-value or significance, as SPSS calls it. And is that less than 5%? Well, indeed, it's less than 1/10 of 1%, right? That's why I put that 0. That really means less than 0.001. So if I look at that, say to myself, well, now I can reject the idea of the equal variances, and I can use unequal variances assumed instead. That that we're going to work with unequal variances. Okay, we're not going to assume that. So in fact, we can use this bottom test instead. Okay, so if I use the bottom test, you can see the t-score is a bit more generous than the top test is, right? So it's I have a bit of an advantage there by using that bottom test, but I can only use it again if I can justify it. Okay, and what is the significance for my t-test? Again, it's less than 0.05, so I can reject my null hypothesis that these two means are the same, and I can accept my alternative hypothesis that the mean age of insured people is different than the mean age for uninsured people. I almost slipped there and used a single-sided test there, right? We remember that as well, that we have to make decisions about whether we're going to do two-sided or two-sided tests. Two-sided tests. And most of the time we're doing two-sided tests. So it's not a surprising outcome. Very big samples and the big difference in the two ages. So that was pretty easy to predict, I think. Okay, so the last test I want to go over is what do we do if we have only categorical variables? Okay, in other words, if we have, for instance, a categorical variable such as insured or uninsured, and perhaps something like gender, which is male or female. So what do I do when I want to determine whether there's a difference in the rate that males and females are insured? Okay, so now we're going to get into a tool that we had. Okay, and before I get to that, I'm going to go back into my variable view and see if I can't organize this so it's a little easier for me to do this. I'm going to take my scalar variable, which was where to go? Oh, I don't want my scalar variable. I want it was number 19. Here we go. There's our insured, uninsured. I'm going to move it up to the very top, so it's a little bit more accessible. Next thing, I'm going to see if I can't find gender. Okay. How about smoker? I'll bet you smoking status is a yes or a no as well. Maybe not. I think it may be 3 values. Never smoked is included. I want a simple one for now. Okay, let me see. Ages and groups. I need to do a search. No problem. Take care. Thanks for stopping in, Ben. And if I probably am not going to get a chance to talk to you guys again. So have a great holiday. And it's been great working with you guys this semester. Take care. Bye. Okay, so let me go back to this. Let me find my variable that I'm looking for. If I can find it here. Let's see. Let me do a search. Know that perhaps sex. Okay, let's see. Okay, sex is sex male or female. That's the one I'm after. Okay. So I'm going to take that variable. And I'm going to move this all the way up here to the top. And I'm going to drop it right up there. So I have two variables I'm interested in working with. And now what I'm going to do is particularly shocking. I'm going to go down here. I'm going to hold down the shift key. I'm going to select all of these. I'm going to ask SPSS to remove them. So now I'm only working with these two variables, right? And it simplifies things for me. Okay, so now each of these variables has a value. I know 1 and 2 represents insured and uninsured. Now I should identify what what numbers 1 and 2 represent for gender. Okay, so I'm going to go back to my code book. Okay, and I'm going to look up the variable sex and see what I find. Oh, sexual behavior. Nope, that's how we want. Let's see, let me try this again. There we go. It's that variable. 1 represents male and 2 represents females. They managed to interview more females than males. Probably is true that there are more females than males in the population. So they would actually adjust based on whether that proportion, adjust all the other results if it involves gender based on the proportions in the population if they didn't really get the correct proportion here. So you'll notice that there are various forms of adjusted outputs in EpiQuery when you take a look at that. And notice that they were also asking the same question for the previous 11 years. So let's see. Okay, 1 is male, 2 is female. So I'm going to go back to SPSS and let SPSS know that the value 1 represents male and the value 2 represents female. And I'm going to click OK. So now I have 2 categorical variables. And I need to organize that data so I can get a look at how these compare, whether gender seems to have any kind of impact, or whether that person is insured or not insured. So I'm going to go into Analyze, and I'm going to go into Descriptive Statistics, because first thing I'm going to do is I want to set this up in a table that makes it easier for me to understand the data. So I'm going to go into Crosstabs. I'm going to create a contingency table or a crosstab. So in my rows, I'm going to put the value which I consider an exposure, or something that's going to cause the other variable to be different. Okay, so I don't think that being uninsured or insured is going to determine some person's sex, but I do think a person's sex might have some impact on whether or not they have insurance. So I'm going to put the gender into rows, and I'm going to put insured or uninsured into columns. Okay, I'm going to go in here to cells. I'm going to start with that. And right now, the only thing SPSS is going to give me is it's going to give me the observed values. It's okay for now. So let's take a look at the observed values. Well, the observed values are interesting. As we said, there's more females than males. And let's take a look. We have 2,900 versus 4,300 insured for males versus females. So we've organized this into a 2x2 table. These are the totals. Organize this into a 2x2 table where I can see the actual numbers. How many males are insured or uninsured? How many females? So I've broken this down or factored it into these 4 boxes. Well, now what I'm going to do is I'm going to take a look at this from the perspective of the percentages by rows. What percentage of males are insured? What percentage of females are insured? That'll give me a bit more information. And in fact, analyze, I can do that in SPSS. I'll just go back to exactly where I was before, except this time I'll go into cells. I'm going to ask it to give me the percentages by rows. Okay, and we create another box, and in this time, indeed, we have percentages by rows. And we can see males, 79% of males in this age group in New York City, 18 to whatever, are insured versus 87% of females. So a higher rate of insurance among females. Right. So now let's take a look at how we might analyze this a bit further. Well, one of the ways that we might do this is a statistic called chi-square, which we discussed earlier in the semester. And the way chi-square works is that we create a new 4x4 crosstab. In fact, SPS will do that for us again. For the moment, I'm going to turn off this percentages by rows. I'm going to tell SPSS to generate two tables for me, the observed values and the expected values. I'm going to click OK. And let's see what I wind up with here. So here's my observed values, these top numbers in each one of these boxes. Usually if you're doing this manually, you might like to make a separate table here. But SPSS puts the expected number in for each one of these boxes in the same box as the previous actual count, the actual real count, their observed values. So how did it get these numbers? Well, the way it got these numbers is that overall SPSS found that 83% of everybody, males and females, 83% of males and females are insured, and are 84%, and 16% are uninsured. So what it did was it said, well, let's see, if there's no difference between males and females, if there's 3,700 males and 86% of them should be insured, then 86% of what I'm seeing here, the total number of males, 86% of them should be in this insured box, right? So multiply that by 80.86, and you get 3116. Notice it's different than the actual value that we observe. Okay? And similarly, we'll do the same thing with females. 86% of them, if there's no difference, the same rate should be applied. In fact, in this case, we find that the actual count is higher than what we would expected if they were insured at the same rate as the entire population. So that gives us an idea that maybe we can compare these observed values and expected values. The more difference there is between the observed values and the expected values, the more confidence that we have that we can say that males and females are insured at a different rate. And you guys remember that we calculate that. Excuse me. You guys may remember that we can calculate that by calculating the difference between the observed values and the expected values, squaring that and dividing by the expected values. In the case of a 2x2 table, we frequently will subtract 1/2 from the difference. In this case, the difference is so big that's probably negligible, but especially for smaller samples, we frequently subtract 1/2. So it's expected values minus observed values minus expected values minus 1/2 squared divided by the expected values. That extra half is called the Yates correction or continuity correction. So at any rate, where we stand now is that, okay, let's do that calculation. So we're going to get a number for this box, which is part of the sum that we're going to use to calculate our chi-square value, a number for this box, a number for this box, and a number for this box. So I'm going to go up to Analyze and have SPSS actually automate that for me. Okay, now I'm going to go with the statistics. I'm going to say calculate a chi-square value. And I'm also going to ask, I don't think I need to look at these expected values for now. I'm going to turn on percentages by rows again, okay, because I want to demonstrate something else as well. Okay, so let's calculate our chi-square values. If you go through these calculations, you wind up with a value of 106. And we know that we are going to, and with the continuity correction, that 1/2 subtracted, it's a little bit smaller, right? It's a little bit more conservative. Difference is negligible for a very large sample. So at any rate, so now I'm going to take a look at that and say to myself, well, is that large enough number for chi-square for me to reject the null hypothesis that there's no association between male and gender and the rate of insurance? Okay, and in fact, what's the probability of being wrong if we reject that null hypothesis? Well, it's less than 5%, as we see here, either with or without the continuity correction. So we've demonstrated with at least 95% certainty, in fact, 99 or better percent certainty, that there is a difference in the rate of insurance being insured for males and females. Well, there's another way that we could express this difference, which is a little bit more descriptive even, and that is the idea of relative risk and odds ratio. Okay, so relative risk is basically a look at the difference between the rate that males are insured and the rate that females are insured. Okay, well, males are insured at the rate of 79%. Females are insured at the rate of 87%. So we can set up something called a rate ratio or a relative risk by taking 79% and dividing it by 87%. And where's that coming from? That's really 2941 divided by 3720, which gives you 79, divided by 4313 divided by 4940, which gives you 87%. So basically 87% divided by 79% divided by 87%. So the relative risk for males versus females is let's see, I'm going to guess about 0.85, right? So you're 85% less likely to be insured if you're a male versus if you're a female in this population. That's your risk of being insured. So another way to demonstrate this, excuse me, another way to demonstrate this is is a is a statistic called the odds ratio. Now, the odds ratio is calculated based on the odds of being insured versus uninsured for each group. Let me clear my throat. Odds of being insured versus uninsured. So that would be based on the number of insured divided by the number of uninsured. Okay, we give you the odds of being insured. If you're okay, I think I can talk for a little while there. Okay, I'm talking for a long time without taking a break. When you have a cold, it's a little bit difficult. So anyway, so uninsured, insured over uninsured, right? That's 2941 over 779. That's the odds of being insured, being in this group or being in that group, right? The relative likelihood of being in either group, divided by the same thing for females. So it's a little bit different. Instead of this number divided by this number over this number divided by this number, it's this number divided by this number over this number divided by this number. These are called odds, right? And the prior was called risks or rates. Okay, so let's calculate what that odds ratio is. Let's take those numbers and actually calculate what they are. And in fact, SPSS does do that for us. If I go down here, the likely, I didn't check it off yet, did I? Analyze, descriptive statistics, crosstabs. And this time, sorry about the hoarseness. So this time I'm going to go into statistics. I'm going to ask SPSS to calculate those numbers. Those are all part of something called risk. I'm going to click OK. SPSS repeats all of the calculations it did before, except this time it gives me the odds ratio for male or female being insured, and it comes up with, is that right? Let me see. Did I do that correctly? Odds ratio for male or female. Oh, yes, it is. Hang on a second. First thing I'm going to talk about is the relative risk. Remember we said the relative risk was 79% divided by, let me take a sip. Okay, remember I mentioned that the relative risk or risk ratio was 79% divided by 87%, which is roughly about 90% or so, 85 or 90%, right? So 0.85 or 0.95 was our relative risk or risk rate. Okay, if I go down here, that's going to be here in my for cohort insured or uninsured, right? It's going to give me my relative risk, which is about 90%. Okay, so now my odds ratio is going to be calculated differently. It's going to be calculated by this divided by this, divided over this, divided by this. The odds for males being insured, the odds for females being insured. And my odds ratio is 0.549. The odds are 55% less likely for males to be insured than for females. A slightly different outcome than we got for relative risk, calculated a little bit differently, but it demonstrates the same tendency. Males tend to be less likely to be insured. Now, let's think for a moment about what our expected outcome would be if there's no association between sex and whether a person is insured or not. Our expectation would be the odds would be the same whether you're male or female. So a ratio of the odds for males or females would be equal to 1. So we would expect the odds ratio and the relative risk, the second line, to both be equal to 1. In this case, they're actually equal to numbers smaller than 1, saying that males are less likely to be insured. Well, since we would expect a value of 1, it would be interesting to have a confidence interval so that we would know whether that result was only true for this sample and it was only due to chance, or if it actually represented the risk, the odds or the risk for the entire population. And indeed, if I look over here, I actually have SPSS has calculated a confidence interval for me. So the odds ratio for males and females is 0.549 in our sample, but we're 95% certain that the true odds ratio for the entire population is between 0.489 and 0.616. So we're 95% sure that it's different than 1, meaning that there's no association. Okay, we got the same result for our relative risk. Our confidence interval for relative risk does not contain the number 1, so we're 95% sure it's different than 1. Okay, so that gives us the same conclusion that we have with our very large chi-square value before, that our null hypothesis that there's no association between gender and the rate of insurance, whether or not a person is insured, we can reject that null hypothesis in both cases, well, 3 cases actually, right? Chi-square, relative risk, and odds ratio. And we can accept the alternative hypothesis that there is, with alpha is less than 0.05, that there is an association between gender and whether a person is insured or not. Okay, so I'm going to leave it at that. Hopefully, you guys have a great holiday. I'll try and post a note, when I'm done with the grading and so on and so forth, when all the homeworks are in. And so maybe I'll get a chance to speak to you one more time again. If not, I hope you've enjoyed the semester. Maybe I'll put up some kind of parting message and maybe a short survey that so I can get feedback on one of them. There is a teacher. I'm pretty sure we're sent notices about teacher evaluations, which they're anxious that you do so that they know whether to how we're doing and like whether or not the format that we're using is successful and so on and so forth. So if you've gotten that notice and it's still available to you, it'd be great if you could do that. I may put a little bit of a survey just so I can get an idea of some of the issues that I'm interested in terms of like whether or not things worked or didn't work, what parts of this worked or didn't work, so I can maybe incorporate it next semester or whenever I'm teaching this former course again. Yeah, and it's been great talking to you guys. I wish we had a chance to have been in a room together and like really meet and speak and so on and so forth. And but I guess that's the main disadvantage of these online courses. I did get to meet some of you. I appreciate you guys making the trip up there. So I wasn't talking to myself at 125th Street, and I'm glad I got to meet all of you guys that did turn up at those things. And again, just so you know, you're not disadvantaged in this course by any means. If you aren't, those were completely voluntary, and they were posted afterwards, so you can view what we were talking about and so on. So you don't have to feel deprived if you weren't able to make those. I know some of you geographically, and because you had conflicting schedules, that was impossible for you to come to. So don't worry about that. So again, have a good holiday season. If I don't speak to you again, finish up whatever homeworks you can. I'll hold off until like Tuesday, as late as I can, probably Tuesday or Wednesday. I'll go back to regrade or take a look at all the homeworks and so on to try and get as much of that in as possible. And good luck in your future endeavors. And drop a note every once in a while to let me know how you're doing. Take care. Bye.